Okay, this is lesson 11.3 on polar calculus. Just keep in mind that polar calculus is very similar to parametric calculus, and there's a lot of similarity between the formulas I'm going to present in this lesson with rectangular equations and the formulas for rectangular stuff that we've been doing in the past, right? So there's a lot of similarities. So try not to memorize the formulas, but try to really see how you can derive or how you can find the similarities and just memorize one. And so then it's useful for rectangular, parametric, and polar. Okay. All right. So the first things first, this one, we don't have an example. It's just kind of a reminder or just telling you that, hey, the derivative, the slope for finding tangent line in polar calculus is this formula right here, where you find the derivative of your r equation times sine theta plus your r equation times cosine theta, and the same derivative again times cosine theta minus r times sine theta. Okay. Now, of course, this is a lot to memorize. So what's another way to do this? Well, keep in mind that derivative is dy over dx, but because these are polar equations, we try to remind ourselves that, hey, polar equations are defined as x equals r cosine theta and y equals r sine theta. So using that idea, I can take the derivative separately and find dy over d theta and find dx over d theta and divide one by the other, thus canceling out or reducing out the d thetas, leaving me with dy over dx. So the way to look at this is to use product rule. The numerator, we want to do dy over d theta. Product rule of this will be the derivative of r, which is r prime, times sine theta, plus keeping the r, and now the derivative of sine theta, which is cosine theta, right? And then your dx over d theta is this one. My derivative of r is r prime again, times cosine theta. And then you keep r, and now the derivative of cosine theta is negative sine theta. And now we have this formula right here, right? That's how this formula is derived, okay? All right, the next one is not as intuitive. So again, figure out how to kind of memorize this or kind of see if there's a similarity here. It's kind of interesting. So it says find the area of the region between the origin and r equals f of theta from alpha to beta. And the formula is 1/2 r squared d theta. All right, so it says find the area enclosed by this beautiful cardioid of r equals 2 plus 2 cosine theta. So you can use the calculator to help you graph this and find the limits or the intervals of your integration. But again, you know, it wouldn't be a bad idea to really know how this is done by hand by knowing the strategic points, right? Find your axis points, find your zeros, your pi over 2, your pi, and your 3 pi over 2. And that will give you a very good idea of what your graph will look like, whether or not you have a limison like the one below where you have a loop inside, or you have a limison without a loop, or you have a lemniscate, which is like an infinity loop. So again, there's a lot of quick ways to figure out what your shape would look like. All right, so you want to find the area enclosed by this beautiful big cardioid here. Now, what it's really asking for is asking for the entire thing. But as we notice here, this is symmetrical, right? So I really don't have to find the entire thing. I can get my integral and my interval set up correctly and just find half of it and double it, right? So what will my area become? It'll be doubling the integral following my formula, alpha to beta. So it starts here at 0. It goes all the way to pi. And how do we know it goes all the way to pi? Well, that number hits 0. So if you set your equation equal to 0, you'll see that cosine theta in the end, it will equal to 0. So theta will equal to pi. So that's my other end of my interval, right? And then your r squared, so your formula squared 2 plus 2 cosine theta squared, and then d theta. Oops, I forgot my 1/2. All right, so as you can probably see now, the reason why I forgot is because you can really take the 1/2 outside and reduce out the 2 outside, right? So you have your 0 to pi, 2 plus 2 cosine theta squared d theta. Now, just keep in mind, most of these can be done by hand, as long as you keep in mind the double angle formula, because if you were to multiply this out, you will get 4 plus 8 cosine theta plus 4 cosine squared theta, and then change out the cosine squared theta with 1 plus cosine 2 theta over 2. You will be able to do this by hand, right? So be in good practice of doing this by hand, but also know how to do this on the calculator, because there's a possibility of this showing up on the non-calc and the calc. So make sure you can do both ways. And if you were to do this by hand, you'll get a lovely answer of 6 pi. If you use a calculator to do this part, you'll get an answer of 18.850 if you round it to 3 decimal places. Okay? All right. Moving on, find the area inside a smaller loop of the limison, this equation here. So I really just want this smaller loop here. So again, keep in mind how we graph polar coordinates is that we graph polar when theta equals 0, when theta equals pi over 3, pi over 4, pi over 6, pi over 2, and then 2 pi over 3, and then so on and so forth. You see how we actually go through this limison this way to get our points, right? So these points above here, it doesn't really matter. It doesn't help me. I need to know when did it cross this axis right here? When did it cross the 0 to start making this loop inside, and then when it crosses again. So basically, I'm looking for when is r equal to 0 in this case. So you do need to do a little bit of work before. You need to set r equals 0 to solve for where my intervals will be. So 2 cosine theta plus 1. So that means negative 1/2 equals cosine theta. Hence theta equals 2 pi over 3 and 4 pi over 3. So those are the limits of my integral, okay? So your integral is going to look like this. You're going to have area equals interval, so integral of 2 pi over 3 to 4 pi over 3, 1/2 r squared 2 cosine theta plus 1 squared d theta. Okay, again, this is completely doable by hand, so you can definitely work this out by getting the exact answer, or you can use your calculator to figure out the final answer. One thing that is true of this is still symmetrical, so you don't have to do the entire interval. You don't have to do it from 2 pi over 3 to 4 pi over 3. If you understand the nature of this, you can actually do it from doubling from 2 pi over 3 up to pi, right? So that will work as well. So either way works. And if you were to work this out by hand, your final answer should be pi minus 3 root 3 over 2. Not a super beautiful answer, but it's very exact, precise, and is about 0.544. All right, so again, check your calculator work or check your hand work and see if you got the same answer. Okay. All right, next one. If you are looking for area between two polar curves, so you really have to read what is being asked of you. In the homework, it gets a little bit tricky because it does ask you in a different way. So for this one, it wants the area in the region inside r equals 1 and then outside of your limison here, cardioid here. So you're really looking for this region here. So then the formula will apply that the outside minus the inside, right? So that would actually work. If my area is asking for this piece inside here, you actually don't do that equation. You don't follow this equation with r squared minus r squared. You actually will take your integral from 0. Sorry, let me make sure that you can see this rule. From 0 to pi over 2 of this blue equation here, and then from pi over 2 to pi of this red equation. That way you get these two separate areas, and then you just double it. So that's if it's asking for this orange piece, but it's not. So it's asking for this for the green piece. So we're going to go ahead and look at the green piece here. Clean up a bit. Okay. Now, as before, yes, this is symmetrical, so I don't have to do the whole thing. I can do half of it again. So I like to highlight what I am integrating. So in my homework for for your reference for answers, I only highlight the region that I am integrating. I'm not necessarily highlighting the region that I'm being asked to do. So don't get confused about that. So yes, even though I'm asked to do the whole thing here, I'm only integrating half of it because I don't want to do that much work. I only want to do half and I can double my answer. Okay. So the key point is finding out what this point is right here. So that is where those two lines cross each other. So we're looking for the intersection. So I'm going to go ahead and solve here. 1 equals 1 minus cosine theta. I'm setting them equal to each other to see what the point is. Yes, you can say that looks like pi over 2, but only by solving it, you will know that's exactly pi over 2, right? So I subtract 1 from both sides, get 0 equals negative cosine theta. So cosine theta equals 0. When is that? Theta equals pi over 2 and 3 pi over 2. So this is my second point here. Right. All right. So my area is going to be 1/2 integral 0 to pi over 2. Right. Oh, and I'm going to double this. So 2 times 1/2. Right. And then outside radius is 1 squared minus the inside radius 1 minus cosine theta squared d theta. Okay. First of all, these reduce out beautifully. And then I would strongly recommend that you multiply this out and subtract because the ones do cancel out nicely, leaving with just the cosine to work with, but there is a cosine squared theta, so you must use double angle formula to change it again. If you were to work this out by hand, you get a lovely answer of 2 minus pi over 4, which is approximately 1.215. Okay, all right, let's move on to the next one. So the next one here is the arc length of this. So arc length in the rectangular coordinate is going to be integral of square root of 1 plus the derivative squared, right? So it's kind of similar. I still have my derivative squared here. The 1 gets replaced by r squared, I'm assuming because my r is changing. But again, I'm not going to claim that I know 100% what is going on here. So you're welcome to look up proofs of how this works. Okay. All right. So same thing as before. If I'm looking for the arc length of this entire cardioid, I don't have to. I can look for half of it. I only want to look for this half, so I can just double my answer, right? So you get, well, before I move on, I'm actually going to find my derivative first because I know I need to find that dr over d theta. So I'm going to work that out first before I plug it into my formula here. So r prime equals, well, derivative of 1 minus cosine theta. Cosine theta is negative sign, so that would be sine theta, right? Okay. All right, so my arc length is going to be double 0 to pi, right? Because it goes from 0 to pi, and then square root of r squared, so 1 minus cosine theta squared, plus you have your derivative now, sine theta squared d theta, all right? So for this particular problem, I would clean it up as much as possible. It is pretty nasty to put this in the calculator, and a lot of things do clean up very nicely. So you have 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta d theta. That would give me 1 plus 1, so 2 minus 2 cosine theta, 0 to pi, 2 d theta. Okay, so this one, I haven't found a way to do this by hand, but maybe that's just because I'm not super experienced in this, so maybe I would need to look it up. But using a calculator, you actually get a really, really nice answer of 8. So that's your answer for this one. All right. Last one is surface area. So just like in our rectangular coordinates and in parametric, you get a slightly different formula if you were doing it with, if the rotation is about the x-axis or the rotation is about the y-axis, right? So here you have the rotation about the x-axis. It is very similar to rectangular coordinates because in rectangular coordinates, your formula was 2 pi y, see y is r sine theta, right? And then for the y-axis, your equation was 2 pi x, and your x is r cosine theta. So it is almost exactly the same thing, and then times the arc length formula that we had from above. So it's the same idea, right? You have 2 pi function times the arc length formula from whichever resource you are doing, which is parametrics or polar, right? Okay, so here it says find the surface area when revolving the right loop of this beautiful lemniscate about the y-axis. So you are go ahead and revolving it around the y-axis. You're going to revolve it this way. You don't have to look for the entire thing. You're only looking for the right loop. So you are going to loop this around, but I also don't need the whole thing because I have symmetry. So I only need half of it. So I only need to find the integration for half of it. And now you can see you are starting at 0 and you're getting to this point right here. You cannot assume that that is pi over 2 because that is where my r equals 0. So go ahead and solve it out and see what my theta is at that point. So when is my r 0? So 0 squared equals cosine of 2 theta. Go ahead and solve this. 0 equals cosine of 2 theta. That means 2 theta equals pi over 2 or 3 pi over 2, but I really only care about pi over 2. So really theta is pi over 4. That means the interval of this particular integral is 0 to pi over 4. All right, so now I'm going to go ahead and use my formula here. I have my arc length. I'm going to double that. So from 0 to pi over 4, I just figured that out. 2 pi r, so r is the square root of cosine 2 theta. And because this is revolving about the y-axis, I need my x value, so I need my cosine theta. Square root of r squared is already defined as cosine 2 theta. All right, but what about my derivative squared? What is my derivative squared? Okay, so the derivative of this, for me personally, I would actually use implicit differentiation. You could go ahead and square root both sides and get r equals root 2 cosine 2 theta. It's just a preference thing that you get the exact same answer. All right, so r squared equals cosine 2 theta. If I were to do implicit, I get 2r r prime equals negative 2 sine 2 theta, right? Divide by 2r, divide by 2r. R prime equals negative sine of 2 theta, and r is root cosine of 2 theta. All right, so again, if you were to square root both sides, you will get the exact same answer. I just prefer this because I don't have to deal with the roots right away. I deal with it at the very end. All right, so that's negative sine of 2 theta over root cosine of 2 theta. Now for this one, I would strongly recommend you clean this up because it actually cleans up beautifully. So first thing first, I would take these out as my coefficient, 0 to pi over 4. You have root cosine of 2 theta here, cosine of theta. I'll combine this into one fraction. So before I do so, maybe it's a lot clearer to see what this squares out to be. So you have sine of squared of 2 theta over cosine of 2 theta, right? And then to write that as one fraction, you do your crisscross applesauce thing, you get cosine squared 2 theta plus sine squared 2 theta over cosine of 2 theta. Yes, this still equals 1, right? You have the same theta and it's cosine squared plus sine squared, so you get 1. So you really have square root of 1 over cosine 2 theta, which is really 1 over root cosine of 2 theta. You still have all this, right? Bring it down. This is root cosine of 2 theta, cosine of theta, d theta, 0 to pi over 4 pi. So these two reduce out. So your equation really gets really cleaned up to be just cosine theta d theta. All right, so plugging this in, what do you get? You actually get a really cool answer of 2 pi root 2, which is approximately 8.886. Okay, all right, so a lot of the calculations here are done really, really quickly. I didn't show you all the algebra, so you're welcome to come check with me later if you want to see all the work detailed out. But make sure your answers are matching up, whether you do this by hand or with the calculator. Okay, that's it.